In Chapter 20, we studied circuits containing resistors and capacitors connected in series and in parallel. The current in these circuits was DC, or direct current, which means the charge only flowed in one direction. Consider a DC circuit in which a capacitor is being charged. Charges only flowed from the battery while the capacitor was charging. Once fully charged, the current in the circuit dropped to zero. However, many devices utilize AC or alternating current, in which the charge flow switches direction periodically. Suppose that the battery connections to the fully charged capacitor were suddenly reversed. Then charge would flow again, but in the reverse direction, until the battery recharges the capacitor according to the new connections. In an AC circuit, what happens is similar. The polarity of the voltage applied to the capacitor continually switches back and forth, and in response, charges flow first one way around the circuit and then the other way. This flow of charge surging back and forth constitutes an alternating current. Thus, charge flows continuously in an AC circuit containing a capacitor. Because the voltage across a resistor or capacitor in an AC circuit changes in time, it's useful to consider the RMS, or root mean square voltage. Recall from section 20.5 that the RMS voltage across the resistor in a purely resistive AC circuit is related to the RMS current by the following. The resistance R has the same value for any frequency of the AC voltage or current. The figure emphasizes this fact by showing that a graph of resistance versus frequency is a horizontal straight line. Now consider a purely capacitive circuit, where a single capacitor is connected to an AC power source. The RMS voltage and current are still proportional to each other, but in Ohm's law, the resistance is now replaced by a quantity known as the capacitive reactance. The capacitive reactance, like resistance, is measured in ohms, and it determines how much RMS current exists in a capacitor in response to a given RMS voltage across it. It is found experimentally that the capacitive reactance is inversely proportional to both the frequency and the capacitance, according to the following relationship. A plot of the capacitive reactance as a function of frequency for a fixed capacitance value is shown in the figure. As the frequency becomes very large, the capacitive reactance approaches zero, signifying that a capacitor offers only a negligibly small opposition to the alternating current at high frequency. In contrast, in the limit of zero frequency, i.e. direct current, the capacitive reactance becomes infinitely large, and a capacitor provides so much opposition to the motion of charges that there is no current. We know that both the current and the voltage change in time in an AC circuit. So let's consider the instantaneous voltage and current, not the RMS, in each of these circuits. The figure shows graphs of voltage and current versus time in a purely resistive circuit. These graphs indicate that when only resistance is present, the voltage and current are proportional to each other at every moment. For example, when the voltage increases from A to B on the graph, the current follows along in step, increasing from A' to B' during the same time interval. Likewise, when the voltage decreases from B to C, the current decreases from B' to C'. For this reason, the current in a resistor R is said to be in phase with the voltage across the resistance. For a capacitor circuit, this in-phase relation between the instantaneous voltage and current does not exist. The following figure shows the graph of the AC voltage and current versus time for a circuit that contains only a capacitor. As the voltage increases from A to B, the charge on the capacitor increases and reaches its full value at B. The current, however, is not the same thing as charge. Current is the rate of flow of charge, and it has a maximum positive value at the start of the charging process at A'. It is a maximum because there is no charge on the capacitor at the start, and hence no capacitor voltage to oppose the generator voltage. When the capacitor is fully charged at B, the capacitor voltage has a magnitude equal to that of the generator, and completely opposes the generator voltage. The result is that the current decreases to zero at B'. While the capacitor voltage decreases from B to C, the charges flow out of the capacitor in a direction opposite to that of the charging current, as indicated by the negative current from B' to C'. Thus, voltage and current are not in phase, but are in fact 1/4 wave cycle out of phase. More specifically, assuming that the voltage fluctuates as V0 sine 2πft, the current varies as I0 sine 2πft plus π/2, which is equivalent to I0 cosine 2πft. Since π/2 radians correspond to 90 degrees, and since the current reaches its maximum value before the voltage does, it is said that the current in a capacitor leads the voltage across the capacitor by a phase angle of 90 degrees. Consider now the power in the circuit, which is the product of the current times the voltage. For the time interval between points A and B, or A' and B', both the current and voltage are positive. Therefore, the instantaneous power is also positive, meaning that the generator is delivering energy to the capacitor. However, during the period between B and C, or B' and C', the current is negative while the voltage remains positive, and the power, which is the product of the two, is thus negative. During this period, the capacitor is returning energy to the generator. Thus, the power alternates between positive and negative values for equal periods of time. In other words, the capacitor alternately absorbs and releases energy. Consequently, the average power, and hence the average energy, used by a capacitor in an AC circuit is zero. As a final topic of this section, we want to introduce a model that will help us in analyzing AC circuits. In this model, voltage and current are represented by rotating arrows, often called phasors, whose lengths correspond to the maximum voltage V0 and maximum current I0, as the figure indicates. These phasors rotate counterclockwise at a frequency f. For a resistor, the phasors are collinear as they rotate, because the voltage and current are in phase. For a capacitor, the phasors remain perpendicular while rotating, because the phase angle between the current and the voltage is 90 degrees. Since the current leads the voltage for a capacitor, the current phasor is ahead of the voltage phasor in the direction of rotation. Note from the two circuit diagrams that the instantaneous voltage across the resistor or the capacitor is V0 sine 2πft. We can find this instantaneous value of the voltage directly from the phasor diagram. Imagine that the voltage phasor V0 in this diagram represents the hypotenuse of a right triangle. Then the vertical component of the phasor would be V0 sine 2πft, which is the instantaneous voltage. In a similar manner, the instantaneous current can be found as the vertical component of the current phasor.